Hello guys, welcome to GATE Success. This video is on Heap Sort. So before understanding Heap Sort, let's have a quick look on the basics of Quick Sort. So before Quick Sort, what we have to understand is what is almost complete binary tree and how it is represented using the array. So let's come to the definition of almost complete binary tree. A binary tree will be a almost complete binary tree if after completing left only it goes to right. That means if if the left is completed and after the left it is going to the right, it will be a almost complete binary tree. For example, you can see in the figure we haven't completed the left one, but we are moving to the right one, so that's why it is a binary tree, but it is not a almost complete binary tree. You can see in the second figure we are moving to the left, and as we have completed left we can move to the right also, so it is a binary tree as well as it is a almost complete binary tree. See this one here, this one is the first point, and what is in the second point, that is after completing the current level. That means look in this third figure, we are on the second level, 0th level, first level, second level. So we are on the second level, but we haven't completed the first level. What is written here? After completing current level, go to the next level, but we haven't completed the current level and we moved on to the next level. Therefore it is not a almost complete binary tree. But in this figure we have completed the current level and we can move to the next level, therefore it is a binary tree as well as it is a almost complete binary tree. If complete binary tree contains k level, if there are k level, then total number of nodes will be what? 2 to the power k minus 1. See in the fourth figure there are 2 level. So if we put it in the figure 4, there are 2 levels. So what it will be? It will be 2 to the power k minus 1. K will be what? 2, because of the 2 level it will be 3. So the total nodes are 3. Similarly, if complete binary tree or almost complete binary tree, complete binary tree will be this and almost complete binary tree will be this. So if complete binary tree or almost complete binary tree contains n node, so n by 2 to the power ceiling will be the number of leaf node, and n by 2 to the power n by 2 to the floor will be the internal. These are few important points which you have to be clear on. Third point is, if complete binary tree contain n nodes and k level, then the number of nodes will be equal to 2 to the power k minus 1 as we have done here. So using this we can find out the value of k. Just one will be came onto the left side, then it will be n plus 1 and apply log on both sides. So k value will what? Log base 2 n plus 1. Representation of binary tree. Binary tree can be represented in two ways. One is with array and another one is with linked list. But the array representation is most important, because array representation is best for complete binary tree or almost complete binary tree. For rest we can use the linked list, but linked list is not very commonly used, so that's why we have to focus only on the array representation. For example, see the first example. In the first example we have a binary tree and we have to represent it in the form of array. For representing it into the form of array, firstly give the numbers to them. What the number will be? 1, 2, 3, 4, 5, 6 and 7. So there are 7 nodes. A will be where? at the first position. Then the left child will be left child of A, that is B, and the right child of A, that is C. Then we have came to B, so we have to complete B first. So the left child of B, so left child of B would be D, so D will be here, and the right child of B will be E, so E will be here. Now we have completed the left one, we have to move into the right one, that is on to the C. So the left child of C will be what? F, and the right child of C will be what? G. This will be the same. Now see this important point, if a node is stored in the ith place of array. For example, let's take 1. If 1 is the ith position, so the left child will be what? 2 into I, that is 2 into 1. So B is the left child. Similarly, we can find out the bth left child. B is on 2, we have to multiply by 2, so 2 into I, that means 2 into 2, 4, left child onto the 4. Similarly, we can find out. So these are three important points for finding the parent, left child and right child in an array. For the second example, let's have a quick look on the second example also. In the second example, D doesn't have a child. In that case, what we have to do is, firstly number them 1, 2, 3. Less, it also has to be, there has to be 2 child. Skip the 2 numbers, it will be 6 and 7. You will understand how I have taken the 6 and 7. So firstly C will be here, and the left child of C will be what? 2 into I, that is 2 into 1, that is on to the second position D. Now the where will be the right child of C? For right child, what we have to do? We have to multiply the sequence number with 2 and add 1, that means 2 into 1, it will be 2 plus 1, 3. On to the third position, there has to be the right child, that means A. Where has to be the left child of A? We can find out using this formula. A is on third position, we have to multiply 2 into 3, that is on the sixth position, there will be the left child of A. Similarly, on to the seventh position, there will be the right child of B. So this way we can find out the position of the left child, right child, all of the parents. So after having the knowledge of basics tree, let's move into the heap tree. What exactly is the heap tree? Heap tree is of two types, that is max heap tree or min heap tree. As I have told you that array representation is best for complete binary tree or almost complete binary tree, it is the same thing. So let's understand about the main heap tree. If in the complete, almost complete binary tree, if the root node is minimum when compared to his children. For example, see here, 0 is minimum when compared to his both children. So it has to be what? It has to be minimum heap tree if it is almost complete binary tree. But you can see we haven't completed the left, but we have moved to the right, so it is not almost complete tree. So because of this particular reason, it is not min heap tree, because it is not almost complete binary tree. Similarly for the max heap tree, for max heap tree also it has to be almost complete binary tree, and every root node has to be maximum when compared to his both of children. For example, in this tree 50 is greater than his both of children, that is it is almost complete binary tree, because we have moved to the next level after completing this level, and it is also max heap. So now let's understand the insertion, how we have to insert into the heap tree. As we can see in this figure, this is a main heap tree because the root is less than the both child. If we have to insert 5, we have to insert 5 into the immediate next location. What will be the immediate next location after 100? So let's number it. It will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 and 19. So we have 19 nodes here and we have to insert 5. So 5 has to be inserted at 20th position. If we insert 5 at the 20th position, so there might be the chances that the order of the particular binary will be damaged or will be violated, because we have min heap here, and after inserting the 5 it doesn't satisfy the property of a min heap. So what we have to do, we have to arrange. How we can arrange? We have to arrange such that the minimum node has to be on upper level. For example, 5 is here and 100 is here. So because 5 is smaller than 100, so 5 has to be above the level. That means 5 has to be here and 100 has to be here. Similarly, now what we have to check, we have to check this, because we have now this 50 and this is 5. Now it has violated the condition, so the 50 has to be here and 5 has to be here. Similarly, now we have to check for further. So the 20 is greater than 5, that means 20 has to be here and 5 has to be here. Similarly, in 10 and 5, 10 is the greater one, 5 is the smaller one. That means 5 has to be on the up and 10 has to be on the low level. So this way we can satisfy the min heap property. So what we have applied here is, min heapify procedure to maintain the min heap property. What we have done here is, we have compared it with this, with this, with this and with this. So we have moved to a particular path. We haven't disturbed the all nodes, we have disturbed a particular part because of the insertion. So there is log n comparison. And how many swaps are there? Because we have disturbed the same path, so there has to be log n swaps also. Because of this, what will the time complexity? It will be nothing but 2 log n, but 2 is a constant, so it will be nothing but order of log n. You can also find out the level. How you can find out the level? As there are 20 nodes, so by placing log 20 to the power base 2, what it will be? The value will be 5. So 5 is what? 5 is nothing but level. First level, second level, third level, fourth level and fifth level. So in this way you can find out the levels. Now let's see using an array how we can do it with the help of array. As I have told you that we have 19 nodes, that means 19 values. The fifth has to be placed at the 20th position. So fifth is placed at the 20th position. Now we have to check 5 with the parent node. So what will be the parent of 5? It will be nothing but n by 2. What is the value of n? It is 20. So 20 by 2, that means we have to check it with the 10th value, that means with the 10th. Because 10th is greater, we have to swap with 10th. Now we have to check the 10th element with his parent. So what will the parent of 10? It will be 10 by 5, that means 5th. So 5th will be the parent. Now because 5 is smaller, so we have to exchange the 5 with this value. Now we have to check with 5 by 2 the floor, which is nothing but 2. We have to compare with 2. So 20 is greater, so that means 20 has to be replaced with 5. Similarly, now we have to check with its parent. So what will be the parent of 5, the parent of 5 will be 10. So as 10 is greater, we have to replace it with 5. So this will be the final sequence 5, 10, 30, 40, 20. So this will be the final sequence which satisfies the min heap property. While inserting an element into a max heap or a min heap which already contains an element, will take order of log n, as I have explained you here, and order of 1 in the best case. If the all is sorted, if we have to place 200, if we have to insert 200, we can insert 200 here, and if we insert 200 here, there will be no violation of min heap property. So in that case it would be the best case. So now let's understand the deletion. We have completed with the insertion. Now let's understand the deletion. For deletion, we have a binary tree. We have a almost complete binary tree, and you can see that it is also min heap. So for deleting 10, what we have to do, we can't delete it directly. So we have to replace the value of 10 with the last value. That means we have to delete 10 and we have to place the value 190 here. And now we again have to run the min heapify procedure to maintain the properties of the min heap. Now check with the childs, whichever child is the smaller, it will be on moved to the top. So 20 is smaller among these three, so 20 will be moved on the top and 190 will be placed here. Similarly, now 190 will be moved with 40 because 40 is the smallest one now. So 190 will be here and 40 will be here. Now 190 is greater than these two and 80 is the smallest one, so we have to move. We have to exchange 80 with 190. Now similarly we have to apply the same thing here also. 160 is the smallest among these three, so 160 has to be replaced with 190. It will be what? 190. So this will be the final answer if we delete 10 from this. Similarly we can perform here also. If we have to delete 10, firstly what we have to do, we have to swap it, we have to replace it with the last element. So we have replaced it with the last element. So let's give them the numbers. So we have to compare with the parents. We have replaced it by this. So now what we have to do is we have to compare 190 with his both of children. What will be the left children? 2 into 1, that is it will be the left children. 2 into 1 plus 2 into I plus 1, that means it will be the right children. We have to check with both of them. So 20 will be the smallest, so we have to replace 20 with 190 and 20 will be here. This is in the array representation. I have made you clear in the binary representation, so this will be in the array representation. Similarly, now we have to check 190, that is the second position, for their children. So what will be the children of second? The children of the second position will be what? 2 into 2, that means 4 will be the left children, and 2 into 2 plus 1, that means 5 will be the right children. So we have to compare 190 with fourth and fifth value, because 40 is the smallest one. We have to replace 40 with 190. Now we have to check for the with the children of fourth element. So what will be the children of fourth? 2 into 4, that means 8 will be the left children. 2 into 4 plus 1, that means 9 will be the right children. We have to compare 190 with 80 and 90, and 80 will be the smallest, so it have to change with, it has to be swapped with 190. Now 190 is here, so we have to check with the children of 8th position. 8 to just 16, so it will be the left one and it will be the right one, we have to again compare with them, and we have to replace with 160 as it is smaller. So 190 will be here and 160 here will be here. So this will be the final answer. Deleting an element from min heap or max heap which already contains an element will take order of log n, as we have done in the insertion also. So in the deletion also, we have moved on a particular path. That means there will be 2 log n comparison, because we have to compare with the both of the children, log n for this, log n for this, similarly log n for this, log n for this. So we have moved to the single path and we have to check 2 element every time. That means 2 log n for comparison and log n for swapping. We have, because we are swapping with only one value, so it will be what, 3 log n, which is asymptotically equal to log n. So it will be the average case or worst case. But in the best case, what we have to do, there might be the chances that we don't have to go to the roots. For example, let's see here, we have to delete 10. For deleting 10, what we have to do is we have to replace it with 80. Now we have to apply the min heapify procedure. If we apply the min heapify procedure, what we do is we have to compare with both of them. 15 is smaller, so 15 has to be here and 80 has to be here. Now we don't have to do further, so it will be the best case. So let's understand build heap method, because we have understand the insertion and deletion in heap. So for building heap, what we have to do is we have to firstly simply make a binary tree with whatever the value is given, and then we have to apply for loop in reverse. For example, we have these values and we have placed in a sequence, that is 25, 30, 40, 50, 15, 17, 19. This way we have placed. So now what we have to do, now we have to check for the non-leaf node, because for leaf node there will be no children, but for non-leaf node there will be a children. So how you can find out the leaf node? We can find out the leaf node by using this formula, and we can find out the non-leaf node by using this formula. Let's name them. So there are total 20 elements. If we find out the leaf node, what we have to do is we have to do 20 by 2 plus 1 to 20. That means the leaf node will be from 11 to 20. That is 11 to 20. These all are what? Leaf node. And for non-leaf node, what we have to do? We have to do is 1 to n by 2, which is nothing but 10. So 1 to 10 is the non-leaf node. So we have to compare for the non-leaf node, as we are applying min heapify procedure here. You can also apply the max heapify procedure, and in the max heapify procedure you have to place the larger one on the upper level, but I am applying here min heap, so I would take minimum number on the upper level. So compare here among 7 and 8, what will be the smallest one? 7. So 7 will be placed onto the upper level and 8 will be placed here. We have to swap the values. Now we have to check for the upper level. So 7 has to be replaced with 15 too, because 7 is smaller than 15. Now as we have made changes here also and here also, so we have to apply on the both of side. So 30 is greater than, sorry, we have to apply in the for loop in, we have to apply for loop in reverse order. We have applied on 10th, 7 is replaced with 8. Now we have to apply on 9. What is smaller? 3. So 3 has to be placed and replaced with 9. Now we have to apply the same thing on 8th location. So 8 is already in the correct position, 10th is the smallest one. Now what we have to do, we have to apply with 7, it is also correct. We have to apply with 6, it is also correct. Now we have to apply with 5, when we apply with 5, the 7 will be replaced with 15. Now we have to apply with 4. Among these three, what we have to do is 3 will be replaced with 50. So 3 will be here and 50 will be here. Now we have to apply with number 3. In this case 70 will be replaced with 40 as 17 is the smaller one. Now we have to apply on the second position. So among these three, number 3 is smaller than all of them. So 3 will be placed here and 30 will be placed here. Now we have to apply the same thing on the first node. So 3 is the smaller, so 3 has to be here and 25 has to be placed here. Now we again have to check in the same manner. That means we have to check from the 10th position, from the last non-leaf node, from 10th to the reverse order. Come to the 10th one. So 15 is greater than 8, so it has to be swapped. Now come to the 9th one. On the 9th position, number 9 will be smaller than 50, so it has to be replaced and 9 has to be placed on the upper level than 50. We have to check at 8th position, it is okay. At 7 it is okay, and at 6, 21 has to be replaced with 40. On the 7th position, it was okay because there is 7, there is 8, it is correct. At the 4th position, we have 9 here, we have 10 here, and we have 30 here. So 30 has to be replaced with 9. Now we have to check at this position. So it is 17, 13, 19, it is okay. Now we have to check here. So 25 will be replaced with 7 because 7 is the smaller one. And now we have to check at the first position, so it is also okay. So similarly we have to apply till the value become sorted. So finally what will be the value? Value will be nothing but 3, 7, 17, 9, 8 will be replaced with 25 because 8 is the smaller one, 25 will be here, then 8, 21, 19, and so on. We have to write it down in a sequence. So in this way you can also apply min happify procedure. If the binary tree is, you can apply anything here because we have to generate the, we have to build the heap. So in the same way you can apply the max heap procedure. So now let's understand the time complexities. How we can find out the time complexity. Time complexity can be easily found with the help of, let's stand in the leaf node. There are m element. If there are m element, so does we need to swap here? No. That means element into swap. Here how many elements will be here? Elements will be m by 2 because it will be just half than the lower level. So m by 2, we can swap it only once, so m by 2 into 1. In the upper level it will be half than m by 2. So what will be the half of m by 2? We can write it as m by 2 square into, we can swap it maximum 2 times. Similarly here, and on to the upper level it will be what? It will be nothing but m by 2 to the power log m, because we are going by 2 by 2 by 2, that's why it is log to the power 2 log raised to m, which into log m, because we are going by 2 by 2. Here we are dividing by 2 and we are here we are multiplying by 2. So what will be the total number of swap? Let's write down from here. It will be nothing but m into 0 plus m by 2 into 1 plus m by 2 square into 2. Similarly, upon 2 to the power log m into log m with base 2. So it will be nothing but 0. If you take m common, we can write it as 1 by 2 की power 1 plus 2 into 1 by 2 की power 2 and so on plus log n into 1 by 2 to the power log m. So we can solve it. It will be nothing but 1 by 2 की power 1 plus 1 by 2 की power 2 plus 1 by 2 की power 3. You can solve it using the GP equations. It is a combination of GP and AP. So you can solve it by them, and after solving this you will get the sequence like this. So it will be nothing but, if you solve it, it will be nothing but 1. So it will be nothing but 1. So what will be the swap? Swap will be nothing but order of m, and comparison will be nothing but 2f, and the total complexity for build heap will be what? Swap plus comparison. It is complexity, it is comparison. How many swaps are there? M, and comparisons are 2m, which is nothing but 3m. It is asymptotically equal to big O of m. If here m will be nothing but n by 2, so it is asymptotically equal to big O of n for all n. So now finally we have to come on to the heap sort algorithm. So firstly what we have to do, we have to build heap, we have to build the max heap, we have to build the main heap, and we have to build the max heap for heap sort. For heap sort we have to build the max heap which will take order of n. Then what we have to do, at the root there will be the maximum element, so we have to delete the root node and we have to place it onto the right hand side, so there will be a maximum value. Now again we have to apply the max cp5 position, and again the maximum will be on the top, again we have to delete it. So in this way, if we delete, the largest will be on the right hand side and the smallest will be on the left hand side. So in this way the whole sequence will get sorted. What will be the time complexity of heap sort? We know that building a heap will take order of n, and deletion will take log n, and we have to do it n times, that means n log n. So it will be for all cases, that means for worst case, average case or best case, order of n log n for heap sort for every case. So heap sort is one of the very important topic in GATE CSE, and there are almost every year a question comes from the heap sort. Either it is of 2 marks or 4 marks. 2 to 4 marks will be definitely from this particular topic. So thank you very much for watching. Please like, comment, subscribe and share with your friends, though you can help them also if they are interested in GATE 2018. Thanks for watching.